Car racing is all about top speed, right? Well, not so fast. Aerodynamic research at the Advanced Wind Tunnel facilities reveals all the invisible forces behind high-tech motorsports.
Aerodynamics is the study of the forces generated by the motion of the body through the air.
There's primarily two main forces on the race car. There's drag, that's holding the race car back, and then there's downforce, that's pushing the car down. We try to reduce the drag so the car can go faster down the straightaway, and then we try to create more downforce so it pushes the car into the ground in the corners.
In the case of a race car like this, which races at the Indy 500, we're trying to balance drag and downforce to produce the fastest lap times. So with racing, it's not about the maximum speed. We're not trying to achieve the highest speed. We're trying to achieve the highest average speed over the course of a lap.
It's kind of weird to think that racing isn't all about maximum speed, but it's true. The secret to a first-place finish is finding the best balance between all the competing aerodynamic forces. A great engine provides powerful thrust to zip the car forward, but the faster you go, the more drag you'll get. So designers and engineers need to find the most efficient balance of these forces. More downforce means more drag. So pursuing that aerodynamic efficiency over the whole track is the key to the trophy. And when engineers strike that balance, race cars can do pretty amazing things.
The drag of this car is low enough that it can reach speeds up to 240 miles an hour. That's going the length of a football field every second. But we're able to produce enough downforce that if the track flipped upside down, the car would be able to stay attached to the road upside down.
A wind tunnel is a facility where we can create a controlled environment where we're simulating wind that blows over the vehicle and how the forces of the wind act on the car. It's like a giant science lab that the engineers use every day to prove out their hypothesis. We have a giant fan that creates that wind speed. We have a section of the tunnel where the vehicle is mounted, and then that just circulates around in a loop.
Think of a wind tunnel like a running track, but with one big difference. On a track, the air stands still while the subject, the runner, moves through it. In a wind tunnel, the subject stands still and the air moves past it, around and around in a big circuit. This makes aerodynamic study possible without having to drive all over town. Wind tunnels aren't new. Back in the day, Isaac Newton dabbled with the idea, and early versions appeared throughout the 18th and 19th centuries. The first enclosed wind tunnel showed up in the 1870s and was used to develop wind turbines and then to study the effects of aerodynamic forces on early aircraft. Research on cars followed soon after, and many modern race car design features are inspired by wind tunnel research. Modern wind tunnels use advanced tech to capture troves of valuable data, nearly all of which are invisible to the naked eye. High-tech load cells, microphone arrays, automated test sequences, and measurement probes allow researchers to pinpoint specific effects and tailor cars for peak performance.
We can control the speed, we can adjust the position of the vehicle, we can adjust the configuration of the car. So we're able to very efficiently learn about the aerodynamic characteristics of the car without going out on a track, use a bunch of fuel, a bunch of tires, go through motors, trying to gather the same data.
The technology is progressing very fast all the time, and in motorsport, we're always on kind of like the cutting edge of it. So what we try to do is always try to find that competitive advantage by using technology, by finding the limits. So when we're designing a race car, we're putting essentially wings like on an airplane, but turn them upside down. That generates the downforce on these race cars. But we don't want to generate too much, because if we generate too much, it creates a lot of upwash and outwash, and that's what creates drag.
This car here is configured to race at the Indy 500, so it has small front wing, small rear wing, generating lower downforce to reduce the drag. But when the same car races, say at Mid-Ohio, or the street circuit at Long Beach, or even the short oval in Milwaukee, it's going to have larger wings on the front and the rear to increase downforce at the expense of increasing drag, but that's going to produce the optimum lap time.
Whoever thought wings would be so important on a vehicle that's never gonna fly? Once again, we see how aerodynamic research allows engineers to design cars that achieve the ideal balance between all the physical forces and interactions experienced on the racetrack. Features like wings, flaps, and contours direct and manipulate airflow at high speeds to minimize impacts of turbulence and drag while generating the optimal speed and downward force for the specific track.
We have a staff of about 19 people, and that goes from the facilities team. They get everything running. We have the operations team that runs the tunnel, as you can see behind me. And then we have our research and development team that looks at that data coming in and making sure it's accurate, it's repeatable, and that's one of the things that makes this building really, really special.
There's a lot of effort that goes into getting a car prepared to go to the race. Almost every week you find out if you've done your job well enough.
It's a competition at the end of the day. Are we winning or are we losing? So it's really exciting to just go and see the car on the track after we put in this work.
You just won the Indy 500, man.